We're constantly hearing about how AI is changing the world, right? But how do we really know if any of it is actually good? Well, it's not about hype. It's about hard numbers. Today, we're going to build this statistical framework to create a real report card for AI so we can finally understand how to grade its performance properly. Let's dive in.
And this is the essential question, isn't it? An AI can write a song or create some incredible image, but how good is it really? Without a solid, consistent grading system, it's all just guesswork and opinion. To get past that, we need a clear set of rules, and that's exactly what we're going to build.
Okay, here's our game plan. First, we'll establish why we even need a formal report card. Then, we'll learn the rules of the game by understanding data and figuring out how to score a single prediction. After that, we get to the really juicy part, the difference between a perfect theoretical score and a real-world score, why our estimates go wrong, and finally, the crucial trade-offs we have to make every single time.
All right, Section 1, the AI report card. Before we can start handing out A's or F's, we all have to agree on what the test looks like. Judging an AI can't be based on gut feelings or just a couple of cool-looking demos. We need a process that's solid, repeatable, and most importantly, fair.
Here's the key idea, and it's a big one. Our intuition about how well an AI is doing can be surprisingly wrong. To get past our own biases, we need a common language and a really clear set of rules, a statistical rubric. This makes sure that when we evaluate any AI for any task, we're all playing by the same rules and the results actually mean something.
Moving right along to Section 2. So now that we know why we need a rubric, let's understand the game the AI is actually playing. At its very core, machine learning is a guessing game based on data. You can think of every single piece of data as one turn in that game.
So every piece of data we have is what we'll call a data point, or Z. Think of it as having two parts. There's an X, which is the input. That's the question we ask the AI. And then there's a Y, which is the output. That's the correct answer we're hoping it gets. Pretty simple, right? Question and answer.
Okay, so that was one data point. Now, let's zoom out a bit. If you could imagine not just one question and answer pair, but the entire universe of all possible pairs, that's what we call the sample space, Z. And here's the critical thing. Not all data points are created equal. Some are really common, others are super rare. That underlying pattern is called a probability distribution, and it basically tells us how likely we are to see any given data point out in the wild.
Okay, we've set the rules of the game. Now let's introduce our player, the AI model itself. It's time to talk about how we actually score its performance, one prediction at a time.
Now, in the language of statistics, we call the AI model a hypothesis, or just H. Don't let the word throw you off. It's just a fancy name for the set of rules the AI uses to get from an input X to a predicted output. You can think of the hypothesis as the student taking the test. It sees the question and makes its best guess. So if the AI's hypothesis is its guess, how do we grade that guess? Well, that's where the utility function, or K, comes in. It's just a simple rule that looks at the AI's prediction for one single data point and gives it a score. It is, quite literally, the grading rubric for just one question on the test.
So how do we build these little scoring rubrics? Well, often, we start with a very simple building block, like this one, the Heaviside function. Don't worry about the name. Just think of it as a simple on-off switch. If you give it a positive number, it switches on and outputs a 1. If you give it a negative number, it switches off and outputs a 0. That's it. It's just a basic way to get a yes or no answer.
And here's a perfect example of how to use that switch. Imagine a simple yes or no question. If the AI gets it right, its prediction matches the real answer. Multiply them, you get a positive number, and our Heaviside function outputs a 1. 1 point. If the AI gets it wrong, you get a negative number, and it outputs a 0. No points. It's a beautifully simple and clean way to score accuracy.
All right, Section 4. So we know how to grade a single answer. But how do we calculate the AI's overall grade on the entire test? This brings us to a really crucial distinction, the difference between the ideal score we wish we had and the real-world score we can actually calculate.
Okay, this split is so important. On one side, you have the Estimand. That's the ideal, the theoretical, true score. It's the AI's average performance if we could test it on the entire universe of data. It's what we desperately want to know, but can never actually get. On the other side is the Estimator. That's our reality. It's the score we actually compute from the limited sample of data we have. It's our best guess at that true score.
Let's put a formal definition on that.
The Estimand, which we represent with the Greek letter theta, is what's called the expected value of our utility function. Now that's just a fancy way of saying it's the true long-run average score the AI would get if we could magically test it on all possible data. This is our North Star, our perfect theoretical target.
And here's its real-world partner, the estimator, or theta hat. This is the actual formula we run on our limited data sample S to get a score. And the entire goal here, the whole point, is to design an estimator that gives us an answer that's as close as humanly possible to that true, unknowable estimand.
So, if our estimator is just a guess at the true score, it can obviously be wrong. And this brings us to the two fundamental reasons why our estimates might miss the mark, something called bias and something called variance.
This is such a great way to think about error. Bias is a systematic problem. Is your measurement on average always a little too high or a little too low? That's bias. It's like measuring with a ruler that's missing the first inch. Every measurement will be wrong in the same way. Variance, on the other hand, is about consistency. If you took a different batch of data, how much would your score jump around? That's variance. It's like trying to measure something with a really shaky hand. And what's really beautiful is how these two types of error come together. The total error of our estimator can be captured perfectly by the mean squared error, or MSE. And the formula is just so elegant. It's simply the bias squared plus the variance. This tells us that to get a good estimate, you have to fight a war on two fronts. You have to minimize both systematic errors and random fluctuations.
Okay, let's bring it all home now. We've defined our data, our AI's hypothesis, how to score it, and the errors in that score. Now we can assemble all of these pieces to see the complete picture, the big evaluation trade-off.
Now, I know this table looks a little complex, but stick with me because it's really a cheat sheet that puts everything together beautifully. Let's just walk through it. Look at that first row. Our estimate is the score we get from our specific data sample. Its long-run average is the mean. Now jump down to the third row. The error is just the difference between our one estimate and the true score. And what's the long-run average of that error? That's the bias. This table shows how every single concept we've discussed fits together, leading all the way down to that final mean squared error. It's the whole story, all in one place.
So, here's the ultimate takeaway. Grading an AI isn't about finding one single magic number. It's a nuanced statistical balancing act. The whole goal is to understand this gap between theoretical performance and practical measurement and to constantly manage that inevitable dance between bias and variance.
So let's do one last quick recap. The AI model itself, we call that a hypothesis. The rule we use to score it, a utility function. The perfect, true score we're always chasing, that's the estimand. The practical tool we use to measure it, that's our estimator. And we always have to remember that our measurement isn't perfect. It will always have some amount of bias and variance.
And that leaves us with a final thought to chew on. If every single performance metric we calculate is just an imperfect estimate riddled with its own potential for systematic and random error, what does that say about our certainty? Can we ever move beyond a well-educated guess to truly know a model's capabilities? It's something to think about. Thanks for watching.